because this problem is too easy for the final. But it's just here for kind of completeness. So the middle of the AM radio band is roughly a frequency of 1,000 kilohertz. The middle of the FM band is about 100 megahertz, right? You know, you listen to 101 point something, 100 is somewhere in the middle. Determine the wavelength of each of these two radio stations. So how would you do that? So, the wavelength of an AM is? 300. How much? 300. 300 what? Meters. Is this the wavelength?
Would you better do here? You wouldn't have any feet room, but it might be better than doing it all.
So FM is in the range of 100 megahertz, so that's 110 to the 6th, and the result is 3 meters. This is why AM and FM behave differently with respect to obstacles. Because all electromagnetic waves are waves. Therefore, they will undergo diffraction and interference phenomena. And the difference between the wavelength of AM and FM makes them behave differently with regard to buildings and things like that. Because if you look at buildings in a city are not separated by 300 meters typically. So you have openings that are small compared to the wavelength of the electromagnetic wave, but they're typically separated by more than 3 meters, and I'm talking about a street that would be used to separate two buildings. And that's why there are very different characteristics for AM and FM radio in cities. Okay? Yes?
If a problem just comes up on the exam, will you specify that we use DSB? Because that only works for a vacuum.
That only works for what?
Vacuum.
Yeah, but it's very close for air, right?
Yeah, but we specify
air is 1.00044 as its index of refraction. So, worrying about being off by 0.00044 is not a big deal. Actually, it's nitrogen that's 1.00044. We'll get an optical boom, which is a flash called Cherenkov light. Now, what sounds weird about that sentence? Faster than light. So nobody can go faster than light goes in vacuum. However,
in different mediums?
Yes, light can be slowed down in different mediums due to the index of refraction. So, for example, in glass, the index of refraction is 1.5, so that light travels at 2/3 of its normal speed. Any particle going through glass faster than 2/3 of the speed of light will make a flash, which is like an optical boom.
Does that mean it's kind of traveling a little backwards in time, or just for that short moment?
No, it's not traveling backwards in time.
Yeah.
Because it's not traveling faster than light does in vacuum. It's traveling faster than light does in the medium. And so you get this little flash. Yes?
Is that really used for the Cherenkov radiation in nuclear reactors?
Yes, it is. In nuclear reactors, what happens is an electron is a very light particle, and so at moderate energy, an electron is a very significant fraction of the speed of light. And since the index of refraction of water is about 1 1/3, then in that case, if you're faster than about 3/4 of the speed of light, then Cherenkov light will be released. And so as you look down into a reactor, the fast electrons are making a water that's a swimming pool reactor glow kind of bluish. And that's Cherenkov radiation. Yeah? Oh, you're saying that the index of refraction of air is a function of temperature? Yes, it is. Yes. The index of refraction is lower when the air is hot because the air, well, okay. Assuming that the air pressure was the same, then the higher temperature is lower index of refraction. Really what you should be going by is the density of the air. So where the air is less dense, the index of refraction is closer to 1. And where the air is more dense, the index of refraction is further from 1. Okay? So that's this problem. Sorry to disappoint you. It's a bit too easy for the final. So,
extra credit. It's gonna be a hard.
Another extra credit.
Yeah. Yeah.
Okay. Now, did I hear people say you should take the easiest conceivable question, too easy for a regular question, and make that as the extra credit? Does that seem logical from a pedagogical standpoint? Yes. Okay. So this is a fun problem. You were hanging around outside your family spacecraft, taking a leisurely spacewalk, and your impetulant kids sped off into the cosmos, leaving you just floating there, about 150 billion meters from the sun.
Wow.
At your location, the intensity of sunlight is roughly 1,000 watts per square meter. That's about how far we are from the sun. But if you think you're going to get 1,000 watts out of a square meter solar panel, don't think so fast because the atmosphere blocks a lot of it. But just above the atmosphere, that's about roughly what the sun is doing here, 1,000 watts per square meter. The gravity is not completely zero, so you start to fall toward the sun. Now, even though it would take you a very, 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 very long time to actually reach the sun, you are concerned that if your position changes a lot, you'll never be found. So you decide to take action, and you make a series of calculations. The first thing you do is you calculate the average, or actually officially this will be the RMS electric field of the light that's nearby. Okay? So, which of these quantities...
Intensity.
Yes, the intensity is what is relating you directly to the electric field. Now, the intensity has what units?
Watts per meter squared.
Watts per meter squared. And we don't typically, or at least, you know, this series of formulas with the intensity and the electric field and blah, 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 there are 100 different ways to write them so that one is dependent upon the other. Typically, the one that I take as my baseline for these kind of calculations is the one that says that the energy per unit volume.
These aren't the lights?
Oh.
Thank you.
Known as U, which is capital U, joules per capital V, cubic meters, joules per volume, is related to 1/2 epsilon naught E squared, 1/2 V squared over mu naught. And how would you compare these two terms? Which one is bigger, 1/2 epsilon naught E squared for an electromagnetic wave, or 1/2 V squared over mu naught? They're about the same, because the energy in an electromagnetic wave is carried 50-50 in the electric and magnetic fields. Therefore, this same expression is equal to double the first term, or it's also equal to double the second term. So if I want to find the electric field of some intense light source, typically what I would wind up doing is first calculating the joules per cubic meter, and then setting that quantity equal to the epsilon naught E squared, then I'll solve for the electric field, okay? So what I was given instead, however, was the watts per cubic meter, and I need to know a relationship that'll get me from here to there and back and forth. So what's the relationship? U times C, because U is in joules per cubic meter as the unit. C is in meter per second. And so the U is I over C. So the intensity of this light was given as 1,000 watts per square meter. Speed of light is 3×10⁸ meter per second. And that number I simply set equal to epsilon naught E squared. And after a little bit of algebra, I'll be calculating the electric field. Now, before I do that algebra, I never remember epsilon naught. I remember K. K is 9×10⁹, right? How is K related to epsilon naught?
Inverse.
1/4
Yeah.
1UI.
So, the way I remember is that 9 times 10⁹ equals 1/4 pi epsilon naught, and then that will solve to tell you epsilon naught. Now, maybe you're different. Maybe you just remember epsilon naught. It's something like, what is it, 8.9 to the minus?
8.85 10 to the minus 12.
Okay. 8.85 10 to the minus 12.
Yeah. What he
Put
said.
in,
What he said.
Yeah, what he said. And then you'll take the square root. Now, officially, if this is a wave, the electric field is actually oscillating. So it's going to go and have some peak value. It's going to go from positive some amount to negative some amount, etc., etc. As a result of this calculation, what am I going to get for my electric field? I'm going to have that E squared equals a number, and then I'm going to have the square root of what E squared is equals a number. So I'm going to have the square root of the typical E squared.